Let us consider getting a metal into useful shape by cold working. If we just start off with the words, we are immediately confronted with the definition of when is cold, or what is cold. If we have a metal and we are working it at room temperature, we consider it cold. It doesn't have to be refrigerated. If we are slightly above room temperature, it's still cold. And we could be at temperatures like 400 degrees and still consider that we are working the material cold for certain materials. So there must be a point above which we are going to call the material being hot worked and below which we are going to say it's cold worked. Before we get to that definition, it's worthwhile to look back at the mechanical properties of the material as we would see them at room temperature. And in the first slide, we see what generally happens in a material if we have a reduction in area. Now let's suppose we're going to reduce the cross-sectional area of the piece by doing something like extruding it, cold extruding it if you please, or let's say we're going to reduce the cross-sectional area by rolling it, or more preferably by pulling it through a wire die. If we did this, then we find that the strength of the material increases and the tensile strength, the ultimate tensile strength, and would move as we go from deformations that are represented by reductions in area, say from here to here, up to about 80% deformation. We find that this ultimate tensile strength continually climbs up and up and up and up and up. Now there's obviously going to be a limit to this, because somewhere we're going to have a tensile strength so high that material is going to be absolutely brittle. We can't deform it anymore beyond that point. Also, you have to notice that we cannot get up to 100% reduction in area, because if we reduce something to 100%, it means we have nothing left, right? So we generally notice that we move up to some particular value and we stop. The yield strength is climbing in the same way as we reduce the area of the specimen, but it doesn't climb as fast as the ultimate tensile strength does up in here. That is, it seems to hesitate. The elongation in the material more nearly copies the yield strength than it does the tensile strength, and you get a curve that looks like this. So the elongation on the material actually is going to hit a minimum when the tensile strength is a maximum, and the yield strength is about the same value it's been for some time. Now in steels, we generally represent all of this in one diagram, and we see a curve, a set of curves that looks something like this. And we see here that we have a plot of elongation, tensile strength, the tensile strength here, the elongation there, the yield strength here, and we have plotted in this as well the hardness. That is to say, the hardness of the material, and this is going to be now the penetration hardness, the Rockwell B scale, Rockwell C scale, or the Burnell hardness more preferably, is going to be looking like that. Not the abrasion resistance, not the modulus of resilience hardness. And so we find that we got a series of curves that just say, in effect, as the strength goes up, the elongation goes down. Or as the strength goes up, the material becomes more and more brittle. Well, I don't know about you, but if I were to look at that curve and had the chance to think about it a long time, one of the first things I'd ask myself is, what in the world is happening inside of the metal that causes the strength to go up? And I would ask the question, would I have the same sort of curve if I was looking at the material at a temperature that would be equivalent to a hot working temperature? What really goes on? So the first thing that we are going to try to face is what happens inside of a metal when you plastically deform the metal. Plastic deformation has three modes, occurs by three modes. They are slip, twinning, and creep. The most prevalent of these in cold working is going to be slip, although the material could also twin. But the creep phenomena is a high temperature phenomena, although a material like pure lead will creep at room temperature, and so we might say, well, we'd have to go to a much lower temperature before we get out of the creep range for that material. But what happens when a material begins to plastically deform at room temperature? What happens when you bend a paper clip? What are you causing to occur in the metal? Well, actually, we know that for most metals, except the amorphous metals we just discussed, but for most metals which are crystalline, we have all of these little islands that are perfectly ordered. That is to say, we have three-dimensional lattice in them. If you considered all of the little points in that three-dimensional lattice, you would notice that you could pass planes through that lattice, and the density of the atoms on the plane would vary depending on the angle we passed it through the lattice. Well, if you experimentally began to wonder what's going to happen when you plastically deform the material, you'd get a single crystal of some orientation. It wouldn't make much difference, and you'd pull on it and see what happened to that one crystal. And what you would find out is that it would deform by slip. And it's just like a deck of cards. On a crystallographic plane, the material will slide. So if you could visualize a big deck of cards, or let's say books in your bookcase that are lying over on the side, and you want them to sit up straight, and they're at rest, they're in equilibrium, and you say, I want to be in equilibrium in another shape. You put your hands on the end, and you squeeze the material, you squeeze the books, then the books are going to straighten up and come to a new equilibrium configuration by sliding on one another. And what we found out over the many years is that metals deform by sliding on specific crystallographic planes. And so, for instance, face-centered cubic materials deform by sliding on the 1-1-1 planes. That's a name that we've given to a certain plane that we pass through this lattice. Actually, there are 4 1-1-1 type planes in each lattice, and it not only slides on that plane, but it's as though it's keyed in a keyway, and it slides in a particular direction. And in the face-centered cubic materials, for instance, like the aluminum, it slides in the 1-1-0 direction, a specific direction. But each plane has 3 of those directions, and so there are 12 slip systems for every little crystal of aluminum. Now, let's suppose that we say we are only going to concern ourselves with one plane, one slip plane. And in the case of zinc, which is a hexagonal close-packed material, we have only one slip plane. If we deform that material, slips only one plane, and it's a single crystal, the slip is uninhibited. That says if it's a bar of zinc and we pull on it, the slip step comes to the surface. It's literally a step. If you were to see a motion picture of what's happening, you looked at the surface, it would be equivalent to watching an earthquake occur when you had big land masses upheave one over top of the other. And that's the slip operation. But in the single crystal, there's nothing to stop that slip except that you stop pulling on it. But if it's a polycrystalline aggregate, and the next crystal to this one that we're going to look at is oriented differently, and it will be oriented differently if it's another crystal, then we have an inhibition of that slip. And so the slip runs into the next grain, right? And therefore it becomes harder. Well, already now we can begin to piece together why the material increases in strength as we cause the plastic deformation to occur. Because as we increase the strength, as we increase the deformation on the material, we're going to change the shape of the crystal. We're going to have more interference in the crystals. We can also see that as the grain size changes, we're going to have a smaller grain size, giving us more interference than a large grain size. In fact, if we have one single crystal, we have no interference. And so we have this, if you please, opposition to the deformation that's occurring just because we have grain boundaries. It isn't the boundary per se that stops the slip, it's the crystal that's next to it. If we have a very brittle material and you force it to do this, to try to slip past that point, it might fracture at that particular point. That is, there's enough pressure on it to cause the material to fracture. And so if you try to bend a piece of zinc that has 2 or 3 grains in it, you'll find you can only bend it so far. When you try to bend it further, the planes can't slip, and so they just come apart, and the material cleaves and gives you a nice shiny surface.
Cold working increases a material's ultimate strength and yield strength, though not to as great a degree, and decreases ductility or elongation. Plastic deformation occurs as slip, twinning, or creep. Grains or crystals offer opposition to slip, causing the deformation to increase hardness of the material. The finer the grain size, the more interference to slip, and therefore the higher increase in hardness and strength from deformation.
I think I explained already to you how the twinning phenomenon occurs, and in coal working we don't have to consider the creep. But what we would really like to know now is what's going to happen to the grain structure as we begin to perform one of the operations, one of the coal forming operations. And if we look at the next slide where we have a rolling operation, a coal rolling operation, which is just like the hot rolling operation now, what we really see is a delineation of the grain boundaries over here in any material. It doesn't make any difference whether this is going to be a steel or non-ferrous material. That is inconsequential. And we roll it and we find that the first thing we do is to stretch each little grain out, and they look like over here. And now you can see that the configuration for the slip interference is going to be different than the configuration that was up here. We have effectively changed the grain size, right, just by the rolling operation. And if you look a little bit further along the line, you find out that in a forging, when you do this, the same sort of thing is going to happen, except now if you visualize that the die, as it closes on this piece of metal, is going to squeeze it like you squeeze the books in the bookcase. We're going to take those little planes and rotate them so they're going to be trying to line up flat over in this piece. Well, something's going to happen here, and that is, since we're trying to make all of the planes line up in this compression piece, like my hands, if we're causing slip to occur, but we're causing the piece to lay over flat, every little crystal is trying to get into that orientation. They can't get into that orientation, but they will approach that orientation. And we call this texture. So it's possible to have a piece of metal, which is cold formed, and also that's hot formed, but a piece of metal that's cold formed that has such a degree of texture that its mechanical properties will be entirely different in one direction than in another direction. It will have become anisotropic, statistically anisotropic, even though if it were random orientations, if there were random orientations of every little crystal, then we would have statistical isotropy. We can roll those or fabricate those and wind up with statistical anisotropy. Well, if we look at the next slide, we find that what happens now, the same sort of modification of the grain occurs in cold extrusion, and from this slide we see that as the ram pushes against the piece of cold metal, has a little equiax grains, it's forced through the die, and during that deformation, slip occurs and the grains become flatter, thinner. That is, in this direction, the grain size is decreased, the interference to slip process is enhanced, and therefore the strength goes up.